Now in this section, our focus is hypothesis testing, which is part of inference. On the previous page, we practiced stating null and alternative hypotheses from a research question. Forming the hypothesis is the first step in hypothesis testing. Here are the general steps in the process of hypothesis testing. So we know the first step, but what are the following steps? First, step one, determine the hypotheses, like we said, the null and the alternative. The hypotheses come from the research question. There should be a research question given, and then from that you can form the null and the alternative hypotheses, kind of like we did on the previous page. Step two would be collect the data. Ideally, we select a random sample from a population, just like we've always talked about. We use data from the random sample to calculate a statistic, either a mean or a proportion, depending on the information given, to summarize the data. Okay, so you know the first and second steps. How about the third step? Assess the evidence. So the next step is to determine if the sample result could reasonably occur when selecting random samples from the population described by the null hypothesis. We use simulation or a mathematical model to describe the probability distribution of sample statistics expected when the null hypothesis is true. And this sounds like a lot of things, but we're just stating them, and then we'll, in the coming pages, we'll go into more detail about each step. Step 4, state a conclusion. We use what we find in the previous step to make a decision. Remember that the simulation or the mathematical model is based on the assumption that the null hypothesis is true. So we're going to assume that it's always true, and then if we find evidence to the contrary, then the alternative hypothesis is true. Kind of like, you know, when there's a trial, you're innocent until proven guilty. So it's kind of like that for the null hypothesis. We're going to assume that that's true and it's innocent until it's proven that it's not true and it's guilty, sort of, I guess. That's a weird example, but oh wait, something like that helps me remember. One possibility is that our sample result is unlikely to occur in random samples from the population described by the null hypothesis. If we think in terms of statistical error, the distance from the hypothesized parameter, the probability is small that the sample statistic has this much error. We conclude that the sample provides strong evidence against the null hypothesis. We reject the null hypothesis in favor of the alternative hypothesis. For example, a sample proportion of 0.68 or greater might be rare when the population proportion is 0.50. Therefore, we can conclude that our hypothesis that the population proportion is 0.5 is incorrect. If this number was a little closer to 0.5, we might say, okay, it might be just random chance that made it a little bit larger or a little bit smaller, but 0.68 is quite a bit larger. So I'd say if your null hypothesis mentions 0.5, that might be wrong. The null hypothesis might be wrong. The other possibility is that our sample results are likely to occur in random samples from the population described by the null hypothesis. If we think in terms of statistical error, the distance from the hypothesized parameter, the probability is large that the sample statistic have a small amount of error. We conclude that the sample does not provide strong evidence against the null hypothesis, so we cannot reject it in favor of the alternative hypothesis. Okay. So another example here, a sample proportion of 0.52 is greater is common in random sampling when the population proportion is 0.50, because 0.52 is fairly close, relatively speaking, to 0.50. Therefore, we can conclude that the sample does not provide strong evidence against our hypothesis that the population proportion is 0.50. We cannot reject the possibility that the population proportion is 0.50, even though the sample proportion was a little bit larger. That could be due to random chance. So let's look at an example, a specific example about data on use on smartphones. According to an article by Andrew Berg, a study found significant growth in data usage, particularly among teens, stating that 94% of teen subscribers self-identify as advanced data users, turning to their cell phones for messaging, internet, multimedia, gaming, and other activities like downloads. The study found that the mean cell phone usage data was 62 megabytes among teens aged 13 to 17. The researcher is curious whether cell phone data usage has increased for this age group since the original study was conducted. She plans to conduct a hypothesis test. So step 1 here, determine the hypotheses. The null hypothesis is often a statement of no change. So the null hypothesis will state that there is no change in the mean cell phone usage for this age group since the original study. In this case, the alternative hypothesis is that the mean has increased from 62 megabytes. So the null hypothesis says it's exactly that. Nothing has changed, but the thought is maybe it has changed and it's gone up. That would be your alternative hypotheses. And they're stated here in a little more detail. H sub 0 null hypothesis is the mean data usage for teens with smartphones is still 62 megabytes. And then alternative hypothesis, H sub A, the mean data usage for teens with smartphones is greater than 62 megabytes. The second step would be collect the data. Okay. The next step is to obtain a sample and collect data that will allow the researchers to test their hypotheses. The sample must be representative of the population and should be a random sample. In this case, the researcher must randomly sample teens who use smartphones. For the purposes of this example, imagine that the researcher randomly samples 50 teens who use smartphones. She finds that the mean data usage for these teens was 75 megabytes with a standard deviation of 45 megabytes. Since the sample mean is greater than 62, comparing those two, it provides some evidence in favor of the alternative hypothesis. But we know that random samples will vary. So how much of a difference will make her doubt the null hypothesis? So in other words, how far apart would the mean from this sample have to be away from the null hypothesis mean in order for us to think the null hypothesis isn't right? Does she still have evidence strong enough to reject the null hypothesis? Well, now let's look at step 3. Step 3, we're going to assess the evidence. To assess the evidence, the researcher needs to know how much variability to expect in random samples when the null hypothesis is true. She begins with the assumption that H sub 0 is true, in this case, that the mean data usage for the teens is still 62 megabytes. She then determines how unusual the results of the samples are. If the mean for all teens with smartphones is actually 62 megabytes, what is the chance that a random sample of 50 teens will have a sample mean of what we got above, 75 megabytes or higher? Obviously, this probability depends on how much variability there is in random samples of this size from this population. The probability of observing a sample mean at least this high if the population mean is 62 megabytes is approximately 0.023. Right now, we don't know how to do that, but later topics explain how to calculate this probability. The probability is quite small. So 0.023, if you think about that, you move the decimal over, that's 2.3. So you only have a 2.3% chance of getting a value that high or higher, 75. The probability is called the p-value. P-value, step 4 would be the conclusion. The small p-value indicates that it is unlikely for a sample mean to be 75 megabytes or higher if the population has a mean of 62 megabytes. It's therefore unlikely that the data from these 50 teens came from a population with a mean of 62 megabytes. The evidence is strong enough to make the researcher doubt the null hypothesis, so she rejects the null hypothesis in favor of the alternative hypothesis. Specifically, the researcher concludes that the mean data usage for teens with smartphones has increased since the original study. That is, it is now greater than 62 megabytes. So let's make a comment here. Notice that the p-value is included in the preceding conclusion, which is a common practice. It allows the reader to see the strength of the evidence used to draw the conclusion. Why do we need a p-value? In the previous example about cell phone usage by teenagers, the sample mean was greater than 62 megabytes. This fact alone does not suggest that the data supports the alternative hypothesis. We have to determine that the data is not only larger than 62 megabytes, but larger than we would expect to see in random sampling if the population mean is 62 megabytes. We therefore need to determine the p-value. If the sample mean were less than or equal to 62 megabytes, it would not support the alternative hypothesis. We would need to find a p-value in this case. We would not need to find a p-value in this case. The conclusion would be clear without it. Because if the sample you took had a mean data usage less than 62, then it contradicts the alternative hypothesis, because the alternative hypothesis said that average teenager is using more than the old thought of 62 megabytes.